when we come across chemical reactions, we're often asked to classify them. Are they acid-base reactions? Are they combustion? Are they whatever? In this particular piece of work, we will be asked to go, is it an reduction reaction or redox reaction? And the most correct way to define a redox reaction is that it's got electrons being transferred from one species, so it might be an atom or an ion or a molecule, to another. But that's really hard to see in a chemical equation. We can't actually see the electrons in that. It's just a balanced equation with the electrons gone. So the easiest way to know straight away if it's redox or not is to assign oxidation numbers to all of the atoms in an equation and go, have any of them changed? And if they've changed, then you've got reduction and oxidation. Oxidation being that the oxidation number for something has gone up, and reduction being that the oxidation number for something else has gone down. You have to have both happen. It's a bit like your muscles working in antagonistic pairs. The bicep only works if there's the tricep. Oxidation only occurs if there is reduction as well. So there's a couple of quick ways to do it. First one is to look, does your equation have any elements? So in the example we had last week, we did have elements, two of them. One's a metallic element and one's a molecular element. So anything that's just one type of atom on its own is an element. And their oxidation numbers, without exception, is equal to 0. There are no exceptions to that. It is 0. So the magnesium has got an oxidation number of 0. The oxygen has got an oxidation number of 0 in this equation. So that's probably the easiest one to do. Then, if I stick with this as our example, the product doesn't have elements in it anymore. It's got two ions, a magnesium ion and an oxide ion. So the next thing we look for is what we call monatomic, mon being one, monatomic ions. And for these, the oxidation number equals the charge of the ion. So in my example here, this is very easy. Our magnesium has gone from 0 up to being a magnesium ion. Doesn't matter that there's two of them. We don't say it's 2 pluses, so it's 4 plus. Each magnesium has got a positive 2 charge, so that is its oxidation state or its oxidation number, positive 2. Interesting if you notice that the sum of these oxidation numbers, 0 plus 0 is 0, is the same as the sum over here, positive 2, and oxides are a negative 2 ion because they've gained 2 electrons. The sum of these is also 0. So you can check pretty quickly if you've got the right number of electrons being exchanged as well by looking at do the oxidation numbers match up. After this, it gets a little bit trickier. We start to get our molecules and our polyatomic ions, and they work by combining a couple of rules. So I'm going to do them as I'm going to say polyatomic species. So poly, many, atomic, many atom, species. Now species can be molecules like H2O, NH4, that sort of thing. Ethanol, so CH3, CH2OH, CH3, CH2OH, or they can be ions. So for example, the carbonate ion, CO3 2-. Now, this rule about the ionic charge will come in for these as well, but there's a few rules we'd go through here. So the first rule you need to know, and this is sort of a hierarchy, the first rule you need to know is that if anything has got more than one type of atom in it, if one of those atoms is hydrogen, hydrogen always equals +1 when it's involved in bonding. It is so tiny that it gives its electron away very easily. All right, as being the mean side of me, because I went to a boys' school, says it's the little weedy boy like I was that got his lunch money stolen from him every lunch because he's so little. I can't do anything about it. There you go. Didn't really happen. It's a story. So hydrogen always loses its electron. So we say that it's positive 1. Okay. There is an exception. There's always exceptions to rules. Okay, there's that little guy who can do jiu-jitsu and no one goes near him because he's gonna beat you. So that little jiu-jitsu guy is called the hydride ion, and he'll grab another one to get 2 electrons. Okay, so there is an exception. So except for what I call metal hydrides. Now, when I was taught this, I went, what the heck do you mean? It's something like, this is quite easy for us with our cell phone batteries. They're often lithium hydride batteries. So that's what I mean. Those hydrogens actually have grabbed an electron off lithium. So, for example, lithium hydride. For those, they've become a -1 ion. So their one is not positive 1, but -1. So a little bit of an exception to the rule. Our next rule, because we work with hydrogen and oxygen so often, is about oxygen. Oxygen has a very high, what we call electronegativity. It'll grab electrons and have a stronger pull on them than almost anything else that it bonds with. Almost anything, which is why, of course, there's going to be an exception to this rule as well. Oxygen, when it's bound with other atoms, is equal to -2. Because it will grab or share 2 electrons with other atoms very, very readily. It's to say what we call a highly electronegative element. Of course, there's an exception, but it's only in one molecule. One molecule breaks the rule. And it's a molecule, of course, we're going to learn about lots this year because it's the exception. So this is a really important exception. By the way, so is this one because they're important in batteries, and we look at batteries in the internal. Okay, so this one has an exception, except H2O2. And I'll talk to you quickly about why this is an easy one to know. The reason is that rule number 1 trumps rule number 2. So if hydrogen's +1 in H2O2, then oxygen must be, sorry if I said that wrong, if hydrogen's +1 in H2O2, then oxygen has to be -1. And the reason is the overall rule that goes with these is that the sum of the oxidation numbers must equal the charge of the species. H2O2 has no charge, so when we add up the oxygen, the hydrogen oxidation numbers, that has to equal 0. So the sum of, I'll use sigma for that, sum of the oxidation numbers has to equal the charge of the species. So that's what we come back to. So you've got this overall rule, and you've got these 2 rules here. Using these few rules, we can actually work out the oxidation numbers of some really complex things like the carbon in carbonate, the manganese in a chemical called permanganate. We could work this one's oxidation number out. And it's a very commonly used one because we know that adding these up, it has to equal -1. We know that our oxygens are going to be -2 because it's not H2O2. And it's got no hydrogen, so rule 1 doesn't apply. So we can apply these rules to find some of this out. Not on the video. I'm going to go through some examples of some ions and how to do this with you, and I'll